Okay, we are looking at these questions from day 1 slides, and we're going to go ahead and do some of them. So, the table shows the results for a mystery spinner. So you know what spinner is. It's just like one of these things where it's got colors all over. So you got yellow, favorable outcomes, and A means the number of times the outcome was, so A can represent yellow, green, blue, purple or blue. And yellow occurred 6 times, 2 times for green, 3 times, ooh, that's a little dark. Let's lower that. 3 times for purple and 1 time for blue. Okay, and determine the experimental probability of the spinner landing on each color. Okay, so let's just do experimental probability. So the way I would do this question would just be to say P of A in all these situations. So this is obviously going to be 6 out of, because NA, PA is equal to NA over NT. And we know this is 2 over, this is 3 over some number, and this is 1 over some number. The question becomes, what is NT? And basically, if these are all the outcomes, well, NT is equal to 6 plus 2 plus 3 plus 1, which is equal to 6 plus 5, or 6 plus 6, which is equal to 12. So it's 12 in all these situations, which is equal to 1 over 4, and this is 1 over 6, and this is equal to 1 over 2. Draw a spinner. Draw what the spinner could look like based on the given data. Okay, so what we have is, we have a circle. This is what our spinner would look like. We have a circle, and half of it's going to be yellow, because 50% of it would be yellow. That's what we expect. 1/4 of it's going to be purple. So let's just grab purple, and 1/4 of the spinner is going to be purple. And then we have 1/6 and 1/6 and 1/12. So essentially how that works is, well, what's 1/12? It's, if we divide this into 3 sections, if we divide a quarter divided by 3, right? If we divide a quarter by 3, what do we end up getting? That's equal to 1/4 times 1 over 3, which is equal to 1/12. So one of these is going to be, the 1/12 is going to be blue, 1/12, and 2 of these, 2/12, 2 over 12, which is equal to 1 over 6, which is here, is going to be green. So a little bit of fraction math, but this is exactly what the spinner would look like. So half of it would be yellow, a quarter would be purple, half the half, basically. And then a third of the quarter is 1/12, that would be blue, and then we have green for the rest of it. Okay, now let's take a look at that. Could the real spinner look different? Yes, it could. This is a communication question. Yes, it could. It could look different because this is just based on an experiment, but we could do an experiment where it could look like this, 5, 3, 3, 1, right? So it could look like this, right? Or it could look like 0. There could be another value here where it was orange, and it turns out to be 1, and this would be 2, right? So depending on the outcomes, that's what we're assuming the spinner would look, but that's not necessarily the case. Okay, that's that for that question. Let's look at this question over here. Helena successfully made 21 out of 30 free throw attempts. What is the experimental probability that she can make successful free throws? So if we talk about let A represent an outcome, we can just say a successful free throw. So we already know that how many successful free throws were there? 21. And NT is equal to 30. So the probability of A is equal to NA over NT, which is equal to 21 over 30, which is equal to, divide by 3, 7 over 10, which is equal to 70%. So the probability of a successful free throw is 70%. If Helena makes 5 out of the next 10 shots, what is her new overall experimental probability of scoring? So if she makes 5 out of 10, well, total we have 5 and 21. So our new NA is equal to 21 plus 5. And out of 10 shots, that's going to be equal to 30 plus 10, which is equal to, let's say 21 out of 5, 26 over 40. All right. Helena says that she typically makes 80% of her free throws. By the way, what is her new overall experimental probability of scoring? It's basically, well, if we do the math, that's equal to, divide both sides by 2, 13 over 20, divide it again by 2, or multiply both sides by 5, and you get 100, and what do we do here? 550 plus 50, 65, which is equal to 65%. Okay, there's two ways we could have done that, right? We could have multiplied by 5, or we could divide by 2 again, which is equal to 6.5 over 10, which is equal to 65 over 100, which is equal to 65%. Right? Now, Helena says she typically makes 80% of her free throws. How accurate would you say this statement is? Justify your answer. I would say not accurate, because at first, when it was 30 free throw attempts, she made 70%. When she made more, it was closer to 65%. So 65 would be more accurate than 70. Now, anyway, there could be more to the mix, but let's just stick to the math. Now, it could be that her first 10 is at 80%, and then it just goes down from there. But let's just say it's not accurate. Next question. An ice cream stand owner. An ice cream stand owner keeps track of his cone sales over a period of several days. The table shows the results. So we have vanilla 9 sales, chocolate, we got 21, raspberry ripple 43, and pralines and cream 78. Determine the experimental probability of a random customer ordering each flavor. Okay, so once again, let's just call this N of A, and we can call this P of A. But what we need to calculate first is, all of these, which is defined as N of T, is equal to 9 plus 21 plus, plus 43 plus 78. Well, that's equal to, okay, let's just do that math. That's 30 together. 43 plus 78 is, or actually, let's do that. That's 73. 73 plus 78. What's 73 plus 78? Well, that's 140 plus 3 plus 8 is 11. So 11 and 151. Sorry how the way I do math. But the answer is 151. If you do it in a calculator, you'll get the same thing. I just don't want to go back in the app between a calculator. So that's equal to 151. And the answer here is 9 over 151. The probability of chocolate is 21 over 151. The probability of raspberry ripple is 43 over 151. And pralines and cream is 78 over 151. How could this information be useful for the ice cream owner? Well, that just means I have to order more pralines and cream than raspberry ripple, and then more raspberry ripple than chocolate or vanilla. It will basically help the ice cream stand owner know how much they need to order and know how they'll run out of, which ones they'll run out of first. Next question. When Sandeep makes her first serve in tennis, she aims for one of the three regions indicated below. These ranges are down the line, middle, outside. That's Sandeep, where they're standing. The table shows the ball placements for several of her previous first serves, not counting missed serves. So it doesn't count missed serves. So determine the experimental probability of each of Sandeep's serve locations. Okay, so we go ahead and determine the experimental probability of each one of their serves. Well, not including missed serves. Well, let's see, that's total number of locations is n. We got to say that's n of t is equal to 3 plus 12 plus 25. And that's equal to 15 plus 25, right? That's 15 plus 25, which is equal to 40. So once again, probability P of A, I'm going to call this N of A. And that's going to be equal to 3 out of 40. That's going to be 12 out of 40. And that's going to be 25 out of 40. So, how does this... So the most probable is, right, the most probable region is the middle. Is the outside right there. And the middle. And down the line is very unlikely. Okay, so what this means is that Sandeep is likely to hit it around here is a good spot to stand. Near the middle or closer to the outside, right? Of course, seeing a player there would affect how they're going to hit, but essentially Sandeep hits it over here. So how could this information be useful to Sandeep's opponent? Well, you know generally where to stand. Okay, done. Okay, a pitcher throws the following pitches in a game. Once again, this is all essentially calculating the experimental probability. Determine the experimental probability that pitcher will throw each type of pitch. Well, essentially, you got to calculate. You have N of A, which is here, for each type of pitch. And essentially, the outcome is that the pitcher throws a fastball. So NA is 86, N of t is equal to 86 plus 8, which is equal to 94. So the probability of a fastball, P of A, oops, let's write that again. The probability of a fastball is 86 divided by 94. Now, if you're looking for percentages, I guess we could do that. Let's see the best way to do it. And then 8.5%, which is 8 over 94. And that's it. How could this information be useful to the batter? Well, we know we're going to get a fastball most of the time, and just be careful for a curveball. Very few times. All right, thinking question. A spinner has 4 colors: red, green, yellow, and purple. The experimental probability of spinning red is 0.2, of spinning a yellow is 0.3, of spinning a green is 0.4. If the spinner was spun 30 times, how many times did it land on purple? Okay, so let's see. So essentially, how this works is, let's say the probability of red, I know I told you letters, but for simplicity's sake, well, we can write a word, right? Is equal to 0.2. The probability of yellow, let's just make it R. Yellow equals 0.3. And the probability of spinning green, is equal to 0.4. Now, the total probability, it doesn't tell me what's the probability of landing on purple. Now, here, we got to think about it, right? The total probability of landing on anything is, remember when we said we could add up probabilities? The probability of landing on red, yellow, or green, remember I used the word green, of red or, I didn't teach you notation for or, yellow or green is equal to 0.2 plus 0.3 plus 0.4, which is equal to 20 plus 30 plus 40, which is equal to, let's say, 0.9. So it's 90% chance that it'll land on these. And there's only these 4 colors. That is 90%, which makes purple 10%. And the probability of purple is essentially 1 minus 0.9, which is equal to 0.1, which is equal to, which is equal to 0.1 or 10%. So, if the spinner was spun 30 times, how many times do you think it landed on purple based on experimental probability? Well, that's easy. It should be 3 times, which is 10% of 30, which is 3 times. And now, finally, we have a paper bag contains 10 colored counters. A counter is randomly drawn and then replaced for several trials. The table shows the results. We have red, 22 reds, 75 greens, 64 orange, and 39 blue. Construct a bar graph or pie chart of the data. with or without technology. Okay, so we'll do with or without technology. Let's go ahead and draw a bar graph. The easiest way I can think of to do this is to just use these numbers right here. Whoops. Okay, we got this. And now we're going to do red happen 22 times. So that's basically 10, 22, and then we'll bring it down. And green happens how many times? 75 times? Green happens 10, 20, 30, 40, 50, 60, 75 times. Orange happens to happen 64 times. So 10, 20, 30, 40, 50, 64 times. And of course, blue happens 39 times. Let's do that. 1, 2, 3, 4. I go all the way to the top because I'm missing one there. All right, that's a bar graph. Now, if I'm doing a pie chart, I'm actually going to have to do, I'm going to have to find out what's 22 plus 75 plus 64 plus 39. I'll just use Siri really quick. So that's all out of 200. So n of t is equal to 200. So we got, that's 22 over 200, or 11 over 100, which is equal to 11%. That's 75 over 200, or 37.5 out of 100, which is 37.5%. This is 64 out of 200, which is equal to, what's 64 out of 200? That's equal to 32 over 100, which is equal to 32%. And of course, this is 39 divided by 200 divided by 2. You get 15 plus 4.5, 19.5 out of 100, which is equal to 19.5%. So if I was to do a pie chart, I'd have to do something like, let's get rid of that. If I was to do a pie chart, it'd have to look like, oops, let's make that black. And what percentage of it is, basically 10%. Let's see, how would we do that? Basically 40%, almost 32 or 33%. So essentially 33% would be orange. So let's get an orange there. And we have, that essentially looks like this. Yeah. And let's see, 19%, so almost 20%. How do we do that? It's just almost a quarter, but just less than a quarter would be blue. Just less than a quarter. 20% would be blue. And then green would be another almost more than a third. So that would be, a third would probably be, oops. Let's see, green would be almost a third. A third would be right there. So more than a third slightly would be green. And red would be the rest of it. So red would be the rest of it. So that's the spinner. Okay. Determine the experimental probability of drawing each color. We already did that over here. Use the result to predict the contents of the bag. Explain your reasoning. Okay, so you just multiply. It's approximately 22, right? Let me just double check. A paper bag contains 10 colored counters. A counter is randomly drawn. Oh, it contains 10. So I do 200. Okay, so I think that if we have 10 for this one, times 11%, or 0.11, is approximately 1, right? It's going to be 1.1, right? But it's approximately, we can't have 1.1 counter, so I would say that we have 1 red counter, right? And then green is about 7.5. We don't know. And this blue is about 19%, 19.5. So 19.5 is approximately 20%, which means if there's 20% of 10, we have approximately 2 blues. And right here we have 32%. I would say that we have 3 counters here. And then obviously that would leave maybe 4 counters here. So total, we'd have 10 counters, which is, that's 5, and that's 5. So that's what I would say. Explain my reasoning, because we did it so many times, and we got a number so close to 1. So our 11% of 200, sorry, 11% of 10 is so close to 1. I mean, for it to be 2, you'd have to have like 19%. No, it's so far away. So that's why I'm very confident in this number. 19.5, essentially the closer you are, it's like 1.95 of them. Like if I multiply this by 10, look, if I do 19.5% or 0.195 times 10, I get 1.9. It's so close to 2, right? I can't possibly be 1. Okay, so that's why it's 2. Very confident in that. Same thing with 32%. 0.32 times 10, right? 0.32 times 10, that's 3.2, right? In order for it to be 4, you have to have so much more, right? You have to have how many more tosses? If there was actually 4, well, if there was 4 times, if it was 4, it'd be 40%. Right? And 40% of 200, I mean, if you looked at it, you'd have to get 80, which is really far from 64 when you have that many trials, right? So the likelihood is that it's got 3 there, and of course, same reasoning for that. Is it possible that your answer to C could be incorrect? Maybe. I mean, but I think I'm very confident in blue. I'm very confident in red. What I'm not so confident is these, but I'm pretty confident, actually. It's possible, but very improbable that I'm wrong. And that's it. That's all the questions that I assigned to you guys.